Yeah, is it clear?
I don't know if I'm right on the board or not. I probably am. I bet it's right here, probably.
Okay. Oh, woo. So what else?
That's what I'm about. All right, here we go. Here we go.
Please. All right, y'all. Go home.
All right, so we're gonna go down through here and see what we have or have not talked about. Okay.
What we have or have not talked about?
Yes.
Good luck.
Never have not.
Everybody's gonna have to be quiet just a little bit, pay attention. I don't have time to say these things.
I'm listening. You ain't gotta worry about me.
All right, if we're trying to pick out a compound that has pi bonding, what are we looking for?
What now?
It's a
If we're trying to pick out a molecule that has pi bonding, what are we looking for? Double or triple bonds, right? Okay.
Oh, yeah.
I want to.
I only realized it earlier today, but there's like no math on this test. That makes me happy.
Oh,
It's a question asked for who has the largest dipole moment in a list of possible choices. What are you looking for?
Electronegativity. The difference of
Looking for the
electronegativity.
most polar one, right?
Yeah.
Okay. So if you have a list of 4 compounds and they say who has the largest dipole moment, they're asking you which one is the most polar, right? Okay, so if you have multiple polar substances in the list, then you've got to look at difference in electronegativity. So the highest difference in electronegativity will be more polar. The simplest way to do that is just distance apart from periodic tables, okay? So like nitrogen and carbon have a difference in electronegativity, but nitrogen and hydrogen have a much higher difference, okay? So the further apart they are on the table, as a general rule, they're going to be more different in their electronegativities. They ask you for which of the following has the shortest bond length. What's the first thing you should try to find?
The third bond.
The triple bond.
Yeah, the triple.
Not
I said
the
third
bond.
bond. I meant triple. Sorry.
Shortest.
I
You're looking for
apologize.
the shortest. You're looking for the triple. If there's not a triple bond, then you're looking for a double bond.
Wait, so if something is more polar, will it be more electronegative or less electronegative?
Electronegativity, you're talking about the difference in electronegativity.
Yeah, you said like the difference.
Polarity comes from the difference in
Basically, who has the
electronegativity between
shortest
2
bond?
atoms.
Yeah, you look for the triple bond first, and then you go to the double bond. And then
You're looking for shorter bonds.
Mr. Kendall, can I ask something? Okay. So let's say you have one molecule that's just a single bond. Let's say all of the choices are single bonded. How would you determine? It would never happen? Okay.
All right, let's see here. So what would this be the definition of? Right here, a lattice of positive and negative ions held together by electrostatic forces. What is the definition of?
Network solid.
It's ionic
No.
bond.
It's an ionic bond, right?
Held together by what now? Yeah, what did you say?
Got-
I have a lattice
got-
of
got-
positive and negative ions held. I didn't get. I
Held together by electrostatic forces. Okay, that is an ionic bond. All right, what is this the definition of? We can't dictate all this. We don't have time. We gotta go much faster than that. Closely packed lattice with delocalized electrons.
Metallic.
It's a metallic bond. Yeah. Okay. Just so we can say we said it. What is the term macromolecule mean? What do you think that?
A big molecule.
Macro means something really big. Those are things like polymers and proteins and DNA. stuff like that, okay?
Ionic compound.
Protein.
Oh, with localized, yeah.
Generally speaking, in general terms, who has the higher melting points? Ionic compounds or covalent compounds?
Ionic.
Generally, it's ionic compounds. Is an ionic compound going to conduct electricity as a solid?
No.
No. How about a liquid?
Yes.
Yeah. How about an aqueous solution as a compound?
Yes.
Yes. Metals will conduct electricity as a solid, though, correct?
Yes.
All right. Question. Does methane contain polar bonds?
No.
Yes.
Yes.
Yes, but it's symmetrical, so the molecule is non-polar, right? The individual bonds are polar, because carbon and hydrogen don't have the same electronegativity. Okay, so methane contains polar bonds that are symmetrical, making the molecule non-polar. Okay, here's, I don't know why I use this, it's so old school, but I guess it's still. Okay, so there's a term called bond order. We mentioned this or not, okay, but bond order is the same thing as like a single bond has a bond order of 1, and a double bond has a bond order of 2, and a triple bond has a bond order of 3. Okay, well, I guess you do know this because this is a big deal in organic chemistry. We get into analyzing resin structures and stuff. It's a big deal. So if they say something has a bond order, which of the following has a bond order of 3, you're looking for a triple bond, right? Not to get beyond this class, but like if something has a bond order of 1.5, that means it's resonant. It's a resonance hybrid between a single and double, right?
Is that the one that like you do that, like the line and then like the
Yeah,
dotted
that's a
line?
1.5. And if you're taking like, if the double bond could be like one of 3 places, it'll have a bond order of like 1.33. But that's not. Fractional bond orders are not a part of this right now.
So what are we looking at?
1, 2, 3.
3 is triple.
All right, you need to be able to, of course, identify hybridizations, right? SP, SP2, SP3, SP3D, and SP3D2, right? That's the hybridizations that we have. And you need to recognize that those match up with electronic geometries, right? That'll help you keep all this straight in your head, I think. If you look down through the table, a couple of pages of the table that we have, the electronic geometries and the hybridizations match. So a tetrahedral electronic geometry is always sp hybridized. Here is always sp, so on and so forth. Okay. All right, let's see. What? Find that. Okay, with alloys, if the atoms in the metallic atoms in the alloy are of similar size, and they're going to be identical, because that would mean they're the same element, you wouldn't have an alloy, right? But if they're of similar size, then they're going to replace each other, substitutional, right? If one of them is considerably smaller than the other, then it's going to fit into the gaps, right? I can't say the word, but interstitials, right? Anyway, yeah. All right, good deal. What does it mean to have a dipole moment of 0?
That means it's non-polar.
Non-polar, okay. Unshared pairs, the same thing as lone pairs, right? So lone pairs and bonding pairs, right? That's the 2 types of electron pairs. Can also be called shared or unshared, right? Same thing, different terms. If we had one of those energy versus distance graphs, right? where's the optimal bond length found at?
Lowest possible.
The lowest point on the graph, right? The dip, bottom of the dip is the distance that the bond would like to be. Of course, it's going to vibrate back and forth between that, like a pendulum swinging through the bottom. Okay, we're talking about boiling points. So they use the boiling point for bonding compounds. A little ridiculous, but that's okay. It's the same pattern. Melting points is a little more practical, right? Lattice energy is another thing that they can use. It all fits together, okay? So the higher a substance who has a higher lattice energy will have a higher melting point, have a higher boiling point. The patterns would be the same. So if they're giving you the boiling point of two different substances, one's going to be bigger than the other. The same one would still be larger if it was melting points or if it was lattice energy. So it doesn't matter which of those three they use as a reference. Okay, just whichever one, doesn't matter. The point is you need to know why the numbers are different. Okay, so it's either about the size or the charge. So if the two compounds are made up of cations and anions, one of them is a +2 -2, and the other one's a +1 -1. +2 -2 is going to have a higher whichever number they're using, right? Okay. If they are same charge, let's say they're both +2 -2s, then the smaller ones will make the higher either melting or boiling or lattice energy, whichever number they're using. Okay. Okay.
Is this the actual test?
Yeah.
All right, now,
This is the actual test. He's doing
okay, how much time do I have?
Keep going. You
Keep
gotta
going.
keep going. Keep going.
Good. Okay, I want to explain something.
42 minutes.
Jeez, really?
Get
So-
out.
No, 32.
Going through the test there, we're not missing anything, okay, so far. So let's add a little something to it that we haven't talked about. It wasn't on there, it needs to be. Formal charges.
Oh, I was so scared earlier.
It's not difficult. So I'm gonna add a question to the test, there's not enough free response on there. I like it to be roughly the same, half and half. And we're gonna grade it half and half, so we're gonna be about half and half, so.
Bonus.
Okay.
Bonus. Are you scaling this test?
Yeah. Well, you know,
No, right away. Or you gonna put a bonus on
here's
this?
what I don't like to do. I did it on the first one because I usually do, but from here forward, I probably won't scale them, but I will have a bonus.
Okay.
I prefer it that way.
So you
What
want
happens when you tell that, and it's a psychological thing. What I've figured over the years happens when you tell people, oh, I'm only going to grade it out at 80% or 90% or whatever, then you only study about 80 or 90%.
Well, then you should have said.
Well, then everybody ends up still making a bad grade. You know what I mean? They figure out that that's what I'm going to do. And they're like, well, to make 100, I've only got to get 80% of them right. So when they study 80%, they end up getting 50% of them right, and end up with the same C they would have made anyway. Right? So we're not, it's almost like giving you permission not to learn all of it, which is not a good idea, because we're not going to make 4s and 5s on the AP exam this spring if we don't learn it. We just get them right and stuff. So we're going to grade it straight up, but then there'll be a bonus question. Okay? All right. Here's a couple of examples of formal charges. Hopefully you watched the video. It must be a pretty good one because several people come in the other day and seem to know a lot about this, just watching the video, which is a good thing.
whatever her name is, Kelly, she was the.
Oh, yeah.
Pootie
was
a
giving.
Pootie don't give. What? I like Pootie. What?
What y'all talking about?
Are y'all talking about
We go AP class. or-
Y'all
Yeah,
like
no,
Kristen?
Pootie was our first video person.
No, Kristen, catch her way. I didn't like her.
Pootie was somebody.
I didn't like her.
I didn't like
I
Pootie.
like Miss.
Pootie was on too fast. I had to go back.
Okay, so here we go. Sulfur trioxide. Okay. Sulfur trioxide. does that drawing meet all the rules? Don't look at formal charges yet if you know what they are. Meets all the rules, does it meet all the rules? Sulfur got all they need?
No, it needs another one.
But at least a double bond right here, right? Okay. Okay, that meets all the rules, right? Okay. Does that one meet all the rules?
It could if sulfur could be expanded.
Okay, it does if sulfur can expand its octet. So the question then is, can sulfur expand its octet? Yeah, because it's on row 3. And if you're a non-metal on row 3, 4, 5, 6, or 7, you can theoretically expand your octet. Okay? All right, so sulfur can expand its octet, so that doesn't break any rules. Okay.
Are we looking at bond angles here with the?
Not yet. Okay, does that one break any rules? No.
No.
Okay, so which one's the right answer? Okay, all right, well, here's the thing. They're all sort of right, but there is a better answer. In this case, there's a better and a best. Okay, there's 3 of them. All right. No matter which one you decide is the better or the best, the geometries and the angles are not going to change. So if you analyze either of these 3, they're all trigonoplanar and 120 degrees. Okay. I got that, sp2 hybridized, and all that's the same. Okay. The difference, though, is if you had the means, you had to get a hold of an X-ray crystallography machine and measure the length of these bonds, what you're going to find is that they're all 3 the same length. Okay, which means that's not the right answer because this one would be shorter than these 2, right? And this is not the right answer because that one would be longer than these 2. These 3 would have the same length. Okay, so that's something that chemists figured out a long time ago. You start measuring the bond lengths of things, and sometimes it's not what you thought it would be. Right? And they figured out there's a pattern to this. And you can figure it out by calculating the formal charge. Okay? So you want formal charge to be 0. Okay? Let me back that up. Sorry. The first thing that has to be true about formal charge is the formal charges have to add to equal the total charge of the molecule. In this case, that's 0, right? Okay? So they have to add to be 0. If they don't, then it's the wrong answer. It's not just not a good answer, it's a wrong answer. Okay? So that has to happen first. And then if you've got that, the best one would be the ones that has as many as possible be individually 0. Okay? If it's a polyatomic ion, they can't all be 0. Somebody's got to be negative or positive to make it add up. But on a neutral molecule like this, probably going to try to get them all to 0. So how do you calculate? Well, there's a big long formula, okay? And then there's a shortcut, all right? So here's the big long formula, just for the fun of it, okay? Formal charge equals, let's see if I can even remember how to write it. So number of valence electrons minus the sum of the shared electrons. Nope, it's half the shared. Hang on a minute. Sum of half of the shared electrons plus all the unshared electrons. Okay, that's the actual formula for it.
Did we do this last year?
Yes, and we did the
Seems
whole
kind of
thing.
familiar.
I remember the best.
Right. So for example, if we look at this sulfur right here, sulfur atom by itself has 6 valence electrons, right? This particular sulfur atom has 2, 4, 6, 8 shared electrons around it. Half of 8 is 4. So we're looking at 6 minus 4 plus, there's no unshared, that's 0, that equals 2, right? Okay, are we with me on that? All right. A double bond, 2 lone pair oxygen. That's got oxygen starting with 6, and it's got half of 4, which is 2, plus 4 shared, that's 0. Okay. This one is 6 minus half of 2 is 1, plus 6 unshared, that's minus 1, which means this one will also be minus 1, right? So that's plus 2 and 0 and -1 and -1, that all adds to be 0. So this is not a wrong answer, okay? But we've got a lot of displacement of charge, they like to call it, okay? Which is not the way molecules like to be. They like their charges to be nice and balanced out, okay? So if it can fix that, it will. If it can't expand its octet, it's probably not going to be able to fix it. Now, there's exceptions. I mean, there's some things can move around a little bit. But normally speaking, if the central atom cannot expand its octet, then you really don't have a lot of options for what you can do. Okay, so if this is not an expandable octet, then there's really nothing to do. Okay, but since it is, we can try some other things. The quickest way to do this, when you're counting around the atom, is just count the 6 minus the tip of every shared, just like 6 minus 1, 2, 3, 4, 5. That's going to be minus 1. Okay. This is 6 minus 1, 2, 3, 4, 5, 6. That's 0. 6 minus 1, 2, 3, 4, 5, 6, 7. That's minus 1. 6 minus 1, 2, 3, 4, 5, 6. That's 0. Okay. I did something wrong. That's plus 1. 1, 2, 3, 4, 5. Yeah, sorry. That's plus 1. Okay. So that still equals 0, but not everybody's 0. So that's better, but not best. Okay. If we go over here, this is 6 minus 1, 2, 3, 4, 5, 6. That's 0. 6 minus 1, 2, 3, 4, 5, 6 is 0. These are all the same. So now everybody's has a formal charge of 0. Right? So that's the best answer. That's how formal charges work. Let's look at another example. The way they're going to ask you this is they give you an example of something and say which of the following is the best answer and explain your answer. You're going to pick out the best one based on formal charges, and your justification is to say, well, this one has the best formal charge arrangement. And you hope if it's the neutral atom, everybody goes to 0, and everybody is 0. If it's a polyatomic ion, then we've got as many zeros as possible. Okay, not everybody can be 0 in a polyatomic ion. All right, so there was one yesterday we saw here. What about, it was like
Oh, yeah.
xenon dioxide, whatever it
Yeah.
is, right? Okay. So this would have 20, right? Or 16, 17, 18, 20. Okay. So that's a decent looking answer, right? Okay. Well, xenon can expand its octet, so what about this? Which one of those is the best? The second. Okay. So what you would like to have is 6 electrons around the oxygens and 8 around the xenon. That would make everybody go to 0, right? Okay. So this is 6 minus 7, so that's minus 1. That's minus 1. And this is 8 minus 6, so that's plus 2. That equals 0, right? But not the best way to do it. This is 6 minus 6, that's 0, and that's 0. And this is 8 minus 8, so that's 0. So everybody's 0. So probably, most likely, if you analyze that compound, you're going to notice that those bonds are a little shorter than what you might predict. And therefore, they're probably double bonds. Yeah.
on the exam, they like deduct points off if we did the first one instead of the second one. Like if they asked us to draw a little diagram of the
If
structure.
they ask you for the best answer, second. Okay. Anytime you're drawing a structure, as you draw it, and the central atom can expand its octet, that's clue number one that you better check formal charges. Because that means there's a lot of different things that could happen. It may be a better choice. And also if they say in the question, where's the best drawing? Then right there, you're thinking resonance and formal charge may be part of this answer. They're kind of giving you a clue that there's maybe more than one way to do this.
Just to be clear, there's no such thing as partial credit on a question in the exam, right?
It's rare. Sometimes there is. It's rare. And they usually don't give but 1 or 2 points per question. If it's a 1-point question, there's no partial credit. If it's a 2-point question, then you'll get a point for something.
So like if it was a 2-point question, it said what is the best structure for whatever, and you gave like a valid structure like the first one, would they give you 1 out of 2?
Yeah, they might. Just give you 1 for something that doesn't break the rules, and then give you the second point if you get the best one.
Can you touch on bond order for just a minute? Like,
Bond order,
what you
okay, so
said?
like this bond has a bond order of 1. So does that one.
And that's two.
This has a bond order of 2, so does
Okay.
that one. How you calculate that is not what we do.
So they go for like the specific bonds, not the overall structure.
They're looking for the best answer.
Well, I just mean, oh, well, if they're saying what's the bond order of the best possible.
What?
I mean, like,
What could they ask involving bond order? Not
What's
not
the
including
bond
that,
order
just in
is?
general, a question they could ask.
Just like what's the bond order of that structure? Or would it be 2? We should do 1 plus 1.
There's 2 different bonds, so it's 2 and 2.
But you can add them, right?
Do you add
No,
them
you don't,
together?
no.
Okay.
That's what
Just say have a,
So,
have a bond order.
so Xenon will have a bond order, well, that whole thing. has
Xenon doesn't have a bond order.
XeO2.
It doesn't have a bond order.
What
The
questions do they
xenon
ask?
oxygen bond has a bond order.
Oh.
This
Okay.
xenon to oxygen bond has a bond order.
Okay.
This
Okay.
xenon to oxygen bond has a bond order.
Oh, so it's separate.
Molecule doesn't have a bond order.
That's what they're probably saying.
Molecules don't have electronegativity either, by the way. They always be have some common mistakes.
They know.
There's no such thing as saying that the electronegativity of xenon dioxide is higher or lower. That doesn't make any sense. This bond, this atom has electronegativity. This one has electronegativity. This one has electronegativity. There is an electronegativity difference between those 2 atoms and a difference between those 2 atoms. But the whole thing doesn't have an electronegativity. It has a polarity. More specifically, numerically, if you want to do math with this, it has a dipole moment. And each of these bonds has a dipole moment, and the molecule has a dipole moment. That's more of a physics problem, mathematical, where you come up with an actual mathematical value of the polarity. That's beyond this class. That would be a physical chemistry topic. Maybe organic chemistry. Where you actually do the vector math and figure it out. But
So, Mr. Chairman, so this one, so this one, so the O to the oxygen and xenon bond, and the second one would be bond order 2. That's it.
it has a sigma and pi bond.
Sigma and pi. Gotcha. So this one, you know, this.
polarity is like,
Taylor, when they ask about like hybridization, does it help if you use their name? Because like I use that, so like
They're
this has.
supposed to take regions of density, but they've used the phrase electron domains. It's probably
That's what
best
I
to use
use.
their phrase.
So like, I know this has 2
Yeah,
electron
they, I
domains.
mean, like, they
180.
can't count that wrong. That's the right, that's what was taught to everybody. Regions.
So did they change it? Do they do?
Yeah, I don't know who decides they're going to offset, use this other term, but who gets to make those decisions.
So now they use regions of density.
That's what they're going to say, most likely. No, they're going to say electron domains.
Okay. That's what I studied.
I have a question.
Where is that?
Can I write it real quick?
What
Can I
is
write it? It's this really like.
Do not chase some crazy graphic. You're just telling me what it is.
I feel like, I mean, it shows like, I can't, like,
Another
maybe
question.
classroom, it was like.
I have a quick question. Oh, yeah.
And then it'll be like this, X, and 90 degrees. How do you want us to like, it'll be like.
What?
Fall.
Is that
That's not
wrong?
90.
Well, I mean, I know that.
Because it's linear.
Because it's linear and what else with the.
That was on
electron scale and stuff like
Yeah.
that.
Oh, if it's linear.
So like, how would I say?
The two oxygen atoms are trying to get as far away from each other as they can, which means they're going to get opposite sides of the carbon atom.
Okay, so.
Where could be,
Wait, what?
what could be something they say macro?
I have no idea.
Every time
Like,
I
figure out, like,
like, like what's something.
Proteins, DNA,
What do you
And
like,
what
in what context is that? Like, how could they?
polymer.
Polymer?
The word is just on the test. It doesn't mean it's the right answer.
Oh,
But a macromolecule is a strand of DNA, a polymer like plastic. So I hold up something like styrofoam, okay? Styrofoam, right? This is all one molecule of styrofoam. It's polymer, okay? It's called polystyrene. They take styrene molecules and link them together. And it's what might as well be infinite strands, okay? And then while it's forming, they blow carbon dioxide into it and makes it puff up, okay? So like the hard plastic would be like on not exactly like those, it's not the same as those plastic bottles, but the hard brittle plastic like CDs. You guys ever seen a CD cover? Maybe there's not, it's a little more brittle than that.
I know what you're talking
Yeah, like a CD cover case, kind of brittle plastic is styrene, polystyrene without any carbon dioxide puffed into it while it's heated. And this, they blow carbon dioxide into it and just puffs it up. It makes what we call styrofoam. Okay? But this is all one molecule of polystyrene. It's a macromolecule. Okay? So it makes a solid piece of stuff. So your proteins, DNA, plastics, things like that are macromolecules.
Now, away from that,
Let's do it.
make sure, like, to make sure I get this, because this is like the only thing that's like, the dipole moment stuff. So if it has the largest dipole moment, it's most polar. So where does electronegativity come into play? I know it's further on periodic table, but like, I need to explain other than just periodic table.
Are both of those polar?
Yes.
Yes. They're both trigonopyramidal, which means they have to be polar, right?
What next one? What was it?
For electrons over
Well, you just said that I was.
They're both polar,
Okay,
they're both trigonopyramidal, which means they have to be polar, right?
okay.
One of them's more polar than the other. In other words, one of them has a higher dipole moment than the other. Okay? So which one is it? It's ammonia. Why?
because it has a higher.
It's on the, it's on the
What?
period above.
Nitrogen has a higher.
Nitrogen. The nitrogen atom is more electronegative than the phosphorus atom, right?
So the nitrogen atom
Okay.
is.
So this is more electronegative than phosphorus. That's just a trend on the periodic table, right? It's higher in the same column, or it's to the right in the same period. This means it's this particular example, nitrogen is above phosphorus in the column, right? That's not what we're gonna say if we're asked to explain why, but that's not on this test. That would have been on the last test. All right, but nitrogen is more electronegative than phosphorus. So this molecule is going to be more polar than this one. They're both polar. They both have a non-zero dipole moment. This one's dipole moment would be a higher value than this one because the electronegativity of nitrogen is higher than phosphorus.
Now, if you do
So
what I'm
these
doing,
individual bonds are more polar. This nitrogen-hydrogen bond is a more polar bond than this phosphorus-hydrogen bond. This is polar, This is more polar.
Can you just draw a sigma for me, please? Just draw a sigma.
You want lowercase or uppercase?
Oh, let me just do lowercase. So.
Are you
if-
referring to sigma and pi bond as lowercase?
Okay, so then, in the triple bond is, there's one sigma and two pi's? Or is there two pi's and one sigma?
A triple would be two pies and then sigma.
Pi's and a sigma.
All right, carry on.
It's a sigma, pi, and a pi.
Can you do a dipole moment of zero for an example of that?
That's the thing.
Dipole moment of 0.
Yeah, an example of that.
There you go.
No, but what helps also is, it's like, you know, like the thing I was telling you the other day.
So how-
Don't have a dipole moment of 0.
What did not?
Is it because it's linear?
Because their electronegativities are the same. That's a simple example of one. Another example would be where the electronegativities are different, but it's symmetrical, so it all cancels out.
The little things, you know what I'm talking about, like the little thing I told you? Just,
Arrows.
yeah, the dipole arrow.
Yes.
If it's symmetrical.
What do you say, arrows on the test?
Difference in electronegativity.
It's just there, just notification.
Polar bonds. That's what this is right here. So these are polar bonds. That carbon-hydrogen bond is polar, okay? This carbon-hydrogen bond is polar, so is this one? Nah, they all are, right? But the arrangement around carbon is symmetrical. So all those polarities cancel each other out. It's like a tug of war. We all pull in one way, but somebody else is pulling the other way, we just gonna stay right in the middle.
Oh, yeah, I caught it. Okay, look, this is what I had on the little thing, on the thing I was looking at, on the AP theme test. It tricked me. It had it like that.
Boron is a special little creature.
And so also, it was like, okay, is this, which one's polar? Like, there was another one that was like this. It had like,
Talk about boron. How much time have I got?
you got 6 minutes. Yeah.
Okay, let's
So
talk
just tell me how
about
that
boron.
works. 'Cause, yeah.
Boron is an exception. Boron forms, stable is a kind of a loose term, but it forms stable molecules with only 6 valence electrons. They're only stable in certain environments, like you can't expose them to anything else. Like, for example, so this is boron trifluoride.
Well, yeah, I forgot the dots.
Yeah, let's not forget the dots. How often not forget, we're forgetting the dots, okay? So that's going to be trigonal planar, right? 3 regions and no lone pairs, that's trigonal planar. But that's only 6 electrons around a boron. Boron can do that, okay, just because God said so, okay? Boron can do that. However, if it is ever exposed, if you had that in a lab, you got to keep that in a flask by itself. You can't mix it with anything else, or chemistry's going to happen, because it don't want to be like that, okay? But it'll stay that way if it's unbobbled. So, for example, if you came upon some ammonia, let's just draw it sideways for a second, okay? What we got right here? Lone pair. So if this compound comes upon anything that has a lone pair, it's going to chemically react, okay? That's going to bond.
Okay.
Okay.
So,
So boron compounds, the boron atom will form a single bond with anything that has a lone pair. Like instantly, just like that.
And that's
That's
just
a very-
boron? That's just boron?
Yeah, boron's the only one that does that. Boron has that 6 valence electron exception.
on the MCQs on that question, it basically asked like which one was polar, or which one was polar. And like, I had like 2 different
Which one
answers.
is, I don't remember which one's what.
But like, it was like, they had C, H, that's not the point, that's not the point. The point is, it's like basically like whenever I was looking at it, I thought that was asymmetrical, since there wasn't an F right there. So like, yeah, like I shouldn't look at it like
It's
that.
literally
Trigonal planar, so it's not.
So just look at the geometry. Okay.
Just follow the same rules as always. So even though boron is an exception, That's still just a 3 region.
Oh, you ain't got no
Very
long
centralized. That's 3 degrees, not polar. It's just highly reactive.
That's 3 electrolytes.
Well, that's what that's
Yeah.
what you said.
Well, before we bonded it, yes.
Let's get close.
Yeah, before we bought it.
1, 2, 3.
That was SPC.
Yeah, SP2, hybridized.
The electrodomain is like, it's helping me, I like that better. I feel like it's worth it to like,
Look at what?
like you can look at that and say,
Yeah,
your
that's how you do
electrodomain
it.
is SP2. Like,
That's how you're supposed to do
I don't know why they're both different.
it. I don't know another way.
On the AP class stuff, there wasn't a lot of, SP3, SP, like, it was just, it went up to like SP3.
Yeah, it was like,
They didn't even show examples of like
You do much
SP3.
5 and 6.
It has a
There wasn't a lot of 5 and 6 electronics.
There won't be a lot of 5 and 6. But there can be some. It's fair game. They stay with the non-expanded test most, it's certainly fair game. I mean, they're throwing on somebody. I mean, that's the kind of stuff like, 4 and 5.
But it will be on the test.
Yeah,
Probably somewhere.
but like also if there's.
All I need is a
Like you see right there.
Okay,
It has all the options.
Are we done yet? I want to back up, but we're not done.
here's one thing you need to be able to do. This is actually easy if it doesn't confuse you. Watch this. Right?
Oh, wait,
Watch this.
I'm watching, but you got to leave my nose? Okay, go.
Or like, if it were something.
Oh, because you're gonna have a question when you're done with whatever you're doing.
Yeah, there was a question like this.
Yeah, I remember that from last year.
Okay, so this is basically like a fill in the blank.
I must.
What they will do with
I love these.
that's not a macromolecule, it's just a little bit larger than, it doesn't have a single central atom, let's put it that way, right? Okay, so often what they will do, they will give you some kind of a clue, maybe, as to how to begin, or they will just give you what I call a skeleton of the molecule, and you're just asked to fill in the electrons, okay? So all you have to do is figure out how many electrons you're trying to fill in. So we've got 2 carbons, that's 6 plus 6 is 12, 13, 14, 15, 16, 22, 28, right? Okay, so we're gonna single bond everything together. There's 2, if I'm trying to make 28 electrons, let's write that down. There's 2, 4, 6, 8, 10, 12, 14. Okay, so now go to the most electronegative element. That's 4, we have 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24.
The carbon.
Carbon, double bond.
25, 26. I didn't count something right. Hang on.
I think it is.
I'm pretty sure you did, yeah.
You said carbon.
It should be 24.
But yeah, I thought it
It
was.
should be
You said
24 carbon.
Counted
So
wrong.
that's it.
Hang on.
But then there'll be a double bond.
No, that's 4 and 4. Yes, it's 24. Sorry, I counted wrong.
Okay,
All right.
messed up.
So that's 2, 4, 6, 7, 10, 12, 14, 16, 18, 20, 22, 24. Okay. So we put the number of electrons in there, right? And then we're gonna look at it for a minute. And here's a rule to remember, okay? In organic compounds, those that contain carbon and hydrogen, okay? Carbon always has 4 bonds and will never have a lone pair. Okay? Let me be technical here. In a neutral organic compound, carbon's gotta have 4 bonds and no lone pairs. That could be 4 singles, it could be 2 doubles, it could be a triple and a single, whatever. It's gotta have 4.
So you have to change that to a double bond?
Yeah, so this right here is automatically wrong.
So
Okay.
we double.
So we gotta do something with that, right? Where's that gonna go?
Can you take it to
Well,
the oxygen that's up there? The, like the top?
You know, there would be a resonance.
I double bonded.
there's still too many electrons.
No, because
Can you take one off the oxygen?
You take one off the oxygen.
That
So like
should've
if you
been
have the
there.
oxygen up
That
front,
one
yeah.
goes there. There we go.
But it's not a resonance structure.
No, no, it's not a resonance.
Really?
So then, wait,
No
my question,
resonance.
can I have a question now?
Can I have a question?
So like if it's,
Oh, yeah.
if it's non-polar, right? What is that, how do you like do?
We're not talking about that.
No,
Okay.
we're talking about like something completely So like if you're looking at the bond, right, and it's like symmetrical structures. And so like if you have ammonia over there, right, and it's symmetrical.
Wait.
No, okay, sorry, the one that's under ammonia.
I'm not feeling good about this.
No.
Methane.
Yes,
That's symmetrical.
so then that would be non-polar.
Yes.
Okay.
Symmetrical means.
Mr. Cato, wasn't there a rule about those drawings like with oxygen? Wasn't there a rule with there's an oxygen bond or something? There's like a.
Or you just remember that carbon's gotta have 4 bonds and no lone pairs, that's pretty much solved.
I have a question.
Here.
And so why couldn't it? Okay, and so why couldn't you do the double bond with the other?
I think it's mainly what
If you do that, you're gonna end up violating.
Like if I moved the double bond to the right and kept the top one single.
You'd be up there too.
For our back.
10 on that oxygen.
Oh,
I'm
okay.
leaving it at home.
So the only way it works is.
Because because the hydrogen are different.
What did you say again? Like this one has 4 bonds because it's a.
Late. Miss Greenlaw.
Okay, wait, I'm apple. Oh, yeah, they asked us. So, like, percentage.
So this one.
I
No
have
percentage. It's just 5 and 6.
What's the bond name?
Am I wrong? Am I wrong? Am I right? Am I right?
This one have polar bonds.
You can go, tell her, I have a quick question.
We're not being able to finish today. Yeah, that's like 120, that's.
Mr. Cato, look, is that right?
Looky.
Karma. Priscilla, my phone is right there. Get my charger back. Because we don't need it.
I'll be all right. We got 8 this farm. I'm good. I know, that's the best one.
I know what everyone is. I can show you every, he's sending me. I'm about to send myself.
Mr. Cato, look at that. Is that right? Like in the one I got in red.
Okay, which one is
Okay.
SP32?
SP3